So let us start with another video where our objective is to go to the determination of motor rating. So let us start with now. Let us take a continuous load. Continuous duty load. A load which is having continuous duty. And let us say the load is, what we see in a load is like it has got a power rating. If I choose a load, the load for that work we need a power rating, and it has got a speed, and then we have got a starting torque. Then we have the load can have like fluctuations in the load, so that can be a transient. There can be a like in a downhill, if the load is going downhill, so there is an option like you need to not give a forward torque, but a reverse torque is required. So let us say that is a reverse torque. Let's see. So you need a reverse torque. So a motor which is capable of having the power rating, so we can have a next higher level of power rating. So motor must be capable of the power ratings, speed, starting torque, transient, and reverse power. This motor can handle all those things, and the power rating whichever we calculate, the motor must have a power. We will choose a motor of next higher power rating, and also the motor must able to sustain the supply voltage, like whatever the nominal voltage available in India, or if it goes to any country, that voltage. What is the standard supply voltage available? It must sustain, and it must have a capacity to run with higher one level higher than the power rating required, speed, starting torque, transient, and reverse torque. All these things the motor must be capable of. And then we choose such type of motor rating. That motor we will choose. So for that, we need to go for a continuous duty type, and let us calculate how to calculate the power rating for a continuous duty type load. And we will see. So when a continuous load power rating, and I say, let us say continuous duty. So here when I say continuous duty, so let us there is an option. Let us take a simple example. The motor is run for let us say this side is current, and this one is the time. It is for certain vibration like this and like this, then this one, then this. Let us take a very simple like this. So it is run up to here, and it is running for the time duration T1, T2, T3, T4, and T5. And with the current over here is I1, I2, I3, I4, I5. So how we can relate it is like 5 different intervals are there, and they are running at a 5 different current. The motor is drawing 5 different currents. So how to determine the equivalent current? Then to determine the equivalent current, we can correlate with the terms of the power loss. So we know that if I will say the power loss will be BC. One is a core loss, another is I square R loss, and I square, let us say this is equivalent current. So if motor is here, it has got these two losses. For an individual interval of I1 and T1, I can say the core loss will be same, and I will say I1 square into T1 This is the individual loss I1 square into T1, I1 square into R, I1 square into R times T1, then again PC plus I2 square R into T2, and similarly we can calculate for 3, 4, 5, and let me write the last one, PC plus I5 square R into T5, and this much, and here I also multiply the total time as T. So relating both the sides, so if I equate these two, I can say these terms are cancel out, the PC into this, so I can say PC common T1 plus T2 dot dot T5, this is 1 plus I1 square T1 plus I2 square T2 plus I5 square T5, and I take R common here, and here I can say PC into capital T plus I equivalent square R into T. So these two terms I will cancel, so I equivalent is equals to I1 square T1 I2 square T2 plus I5 square T5 whole divided by capital T. So this is what I can find the I equivalent. So what is the conclusion remark is here that in a continuous load we can calculate what is the equivalent current with individual current squared multiplied by the time for which it is applied and divided by the total time of running. So like that we can calculate what is the equivalent current. So once I know the equivalent current, so I can find equivalent current square into R. This is the copper loss, and with the core loss, rating these two, I can find what is the power rating required. So from here I can say what is the power rating. This curve can be, I can have a continuous line like this for time t up to h. So here I can say again rating I equivalent is equal to root over of root of 1 by t integration of 0 to t I square dt, where I is the current from 0 to t times capital T is the time up to which we are calculating, and like that we can also calculate what is my, like that we can also calculate what is the equivalent current if the current is given in terms of continuous term. In this way we can calculate the equivalent current. So what is the plus point of this is that from the equivalent current we can calculate what is the power rating required. And let's see next that here one is the important point is that we are taking the assumption, like what is the assumption is that heating and cooling conditions remain same. But we know that the cooling condition will not be remain the same. It depends on the speed. If the speed is high, the cooling will be faster. If the speed is less, the cooling will be slower. So that's the thing. Another thing is this, after getting the I equivalent, directly we cannot calculate the power rating. What is the problem? Let us see. There is another called overloading factor. That DC motor, suppose we say DC motor, and the current rating is say 10 ampere. What is the thing is that I can exceed the current rating to 20 amperes for a short duration. I can exceed the current for a short duration. So that how we can relate that, we can say lambda should be greater than equal to I max by I rated. So here I max is 20 and I rated is 10. So rating of the motor is 10, but there is also a maximum current that I can give to the motor is 20. So the lambda value is 2. So how this helps that the now rated value is calculated indirectly from I max by lambda. Now this helps me to calculate what is rated value. So I max is, let us say, 20 and lambda is 2. Now I can say the I rated is equal to this value is 10. So this is how I calculate the rated current. Now for induction motor, this lambda is 1.65 to 3, and for synchronous motor this lambda is equal to 2 to 2.25. For specially designed synchronous motor it can be up to 3.5. So this overloading is important. Here also induction motor, how much maximum current we can give, this can determine from the. So what is important finally is that the final important thing is that let us you choose what is the maximum current that machine can sustain, and then find out what is the safety value you will keep. You want to lambda. So let us say lambda maximum current is say 20 amperes. Lambda you choose at 2. So your rating I rated will be equals to 20 by 2, 10. So this is how we calculate what is the rating of the motor. So here for continuous load it is okay, but for the short time duty load this is not okay, because here the maximum current will be not 20, the maximum current can be like 50 amperes. With the lambda 2 the rated current will not be that. So this is only for continuous duty loading, for only for continuous duty loading. Okay, thank you very much.